I am Ryan Blue. I am the co-creator of Apache Iceberg, and I currently work at a company called Tabular that provides basically managed Iceberg service. So everything from Trino down the stack. We don't actually provide Trino. Starburst does that. So yeah, really excited to be here today. Today we're going to talk about something that's been coming up more and more, basically CDC patterns in Apache Iceberg. So we're going to cover basically like how I think about CDC patterns, some of the things that we've done in the past at like Netflix, and what I think the best practice and like emerging patterns are for CDC in Apache Iceberg. So thank you all for being here. Oh, and one more thing. I'll give you a couple seconds to scan the QR code here, where we have Iceberg cheat sheets for both Spark and Trino. And there are a ton of other helpful things on that website. We've got like a workshop for learning about data warehousing in Starburst and Tabular and things like that. So encourage you all to go there and explore a little bit more. But with that, let's dive into the actual content and talk about, Iceberg. Oh, my slides aren't changing. There we go. What is Iceberg? What is CDC? And sort of why are we here? So as you probably know, Iceberg is a table format, which means it's basically taking a whole bunch of files stored in an object store like S3 and giving those files a way of achieving SQL behavior, ACID semantics, schema evolution, and so on. So it's really all about how do we keep track of what is in a table and have really high quality ways of working with table data, even though it's just a whole bunch of files in an object store. The other aspect of Iceberg that's really exciting and important is that it's an open standard. So Iceberg is something that is getting built into BigQuery and Snowflake and Starburst and Athena and EMR and all sorts of commercial database offerings. And that's because it's open. Anyone can participate. We want this to be something that no one owns so that we have a common data layer sitting underneath all of those, really great open source and closed source databases. What we're here to talk about today is CDC, which is change data capture. CDC is basically the idea that as you make changes to a relational or transactional table, you should be able to easily get the update stream from that table and use that for downstream things like updating a search index, or what we're going to talk about today is putting that data and using it into a analytic table, basically using it to make incremental updates to an analytic table where you want to be able to do massive queries using a parallel system like Trino or Spark. And you might be thinking, well, why do we care about, why don't we just go query that database directly? Which is, I think, a big part of understanding why you would want to do CDC. It's very lightweight on the source database. If you start hitting a source database that's, say, running your production application with a parallel system like Trino or Spark, it's very, very easy to take that database down with a simple misconfiguration. So say everything's running fine in production for a couple of weeks. You're able to go do your analysis, hit that table and query it as you need to. And then you say, this is great. I want to move the last month's worth of data into this pipeline. And you run the pipeline 30 times in parallel, once for each day. And now you've gone and made the load on that production database 30 times higher. It's just very, very easy to take down a production database and cause an outage and get yelled at. Your SRE team is never happy when you do that sort of thing. And so rather than being super careful with what we run on the database, what we want to do is just make a copy of it very easily and maintain that copy. The question is, how do we do that? And before we dive too far into that question, I want to just introduce the example that we're working with today so that you can sort of see what's going on. So our example today is going to be a bank. Say we're running a bank. It seems like anyone can do it these days. So we're going to run a bank. And what we have is a transactional database with an accounts table where we have the account ID and a balance for that account. What we want to do is, again, so we don't take down the bank, kind of a mess if customers can't access their money, we're going to create a mirror table in an analytics store, and specifically in Iceberg. So this is what it looks like over here on the right. We have this table accounts that has the exact same structure as the original source table, but then we can add on these things like specifically bucketing or partitioning the table so that it is easy to update. We can also do things like set the primary field keys, like account ID in this case, and we can also change the layout and the ordering so that things are clustered for better performance later on. Now, our goal with this table is to keep it up to date using incoming transaction data from the actual source of truth database. So that's what we're going to be doing today. That transaction data looks like this. It's basically every time something changes on that original database or that table, we get a record of which row changed and how it changed. Now, this looks like double entry bookkeeping because that's exactly what it is. Each time a bank account changes, that's a transfer. And we get two sides of that transfer. So for any given transaction ID, say transaction 2 here, where account number 2 sent account number 4 $863, we get two entries. We get one that subtracted $863 from account 2 and one that added $863 to account 4. Now that's really important on the original table, right? That we don't either destroy money or create money at will, because this is happening in a transaction. And it says, hey, if account 2 doesn't have $863, this transaction doesn't go through. But more importantly, we keep consistency, where when that transfer happens, account 2, the change to debit account 2 and subtract that money happens at the exact same point in time as the change to add the money to account 4. That's why they have the same transaction ID. Now, at the end of the day, this double check here down at the bottom should always be true. Because we're only transferring money between accounts, the sum of all balances in accounts, that is like the total deposits at the entire bank, should never change. In other words, like a bank should neither create nor destroy money. If a bank accidentally loses track of money, that's really bad for the bank. On the flip side, if the bank creates money from thin air, regulators get a little angry. So the deposits should always be reliable. And I think the key thing to remember here is that if we're using this table for analysis, we actually want it to also be reliable. So not only does the source table have to have this property that we don't create or destroy money, we want our downstream analytic table to have the same property. We should never see this table in a state where it's just completely out of whack. We refer to this as transactional consistency, where the state of the mirror table is always consistent with transactions in the upstream table, where you get, essentially, if you're reading the mirror table, you should always get a point in time for the upstream table. Now, it might not matter what point in time you get, just that, you don't see the half applied transactions really. I should also mention the source of this transaction data is not really what we're going to cover today. This is typically something like AWS DMS or Debezium. Here, I modified it a little bit because those produce like UPSERT kind of records. And I want to highlight the fact that you're not always working with UPSERT data. Sometimes you're working with data that looks like this, where you get a stream of, diffs against a table, and you have to read the original data to actually apply that. It also makes some of the queries later on a little easier to understand, so we're going with this model. So that's basically our setup, right? We're running this bank, and all of the patterns are going to be looking at how do we apply this set of transactions and keep the downstream table in sync in an incremental fashion. Now, why is that a hard problem? You might think, oh, hey, that's easy, right? You just go run an update on the table. But it's a surprisingly hard problem, and it's surprisingly hard for a number of reasons. People's expectations of this data are really high. So first of all, people sort of expect to have the upstream table and the mirror table, and you just write directly to the mirror table. What could be so hard about that? That way we write to the same table we read from, and everything is good. Well, that actually is at odds with some of the other patterns, or you end up trading some other properties that we want to look at. So the next thing is you want a completely accurate historical record. You want to be able to go to the mirror table and read back all of the changes that were applied, so that you can run CDC downstream maybe, or so that you can simply audit that you got all of the changes. You also would love, and this isn't necessarily something you can do, you'd love to be able to time travel to any point in time. If our changes look like this, where I have an increasing transaction ID, what's to stop me from going to, say, transaction 2 and reading the state of the table at that time? Ideally, we would be able to time travel to the result of any transaction on that table. Consistency, I just went over. We want to make sure that when we read the mirror table, we only ever see transactionally consistent states of the upstream source table. We want to be able to just pump a lot of data in there, and we want it to happen immediately, which is always a problem. We never want to pay the penalty on reads. We never want to pay a penalty on writes. And what's more, probably the simplest problem on here, just because it's been solved for years, is schema evolution. So another aspect of CDC that you do not want to overlook is, how is the schema in the source table changing? And can I actually mirror those changes in the mirror table? If your data format, unlike Iceberg, doesn't support schema evolution, then you can get into situations where you're actually corrupting the mirror table and getting into a bad state, just simply trying to match the operations on the upstream table. When you say drop a column or rename something, or drop a column and add it back, things like that can really mess up your data. Luckily, we're not going to cover schema evolution very much, because Iceberg supports all of the schema evolution that can happen in the upstream tables. So let's look at why this is hard. Where are these desires or requirements at odds with one another? Well, first of all, they're just problems like lower latency. If you want to update your mirror table every minute, that just means you're creating more and more work, because you need to, say, rewrite an entire data file to update a single record in that data file. Well, if you're doing that every minute, you're rewriting that data file every minute. If you're doing it every 5 minutes, then you're doing it 20%, 1/5 of what you were before. Then there is a problem of write amplification. So when I want to make changes to my table, to my mirror, do I need to actually rewrite whole data files? Or can I put off some of that work, delay it until later, so that I don't redo the same amount of work? In general, these two things are separate. Lower latency means more work in general, even if you have low write amplification. Write amplification is how much work it takes to balance the trade-off between efficiency at read time and efficiency at write time. Then we have the fact that all of the changes to an analytic table, like Iceberg tables, Hive tables, whatnot, are batched together. These are not formats where we can go and make very fine-grained changes to a random access file. Because this data is stored in S3 or some other immutable data store using immutable formats, we have to think about clever ways to make changes to those files. We also have large batches, and that brings in, what do we do if we have 2 updates for the same record in a single batch? If you have the double update problem, then you can't have an accurate historical record. You can't time travel to any point because you necessarily can only have 1 copy of a row coming out of a batch. So if it changed 2, 3, or more times within a single batch that you're applying, you simply lose the accurate history and you lose the time travel. Another thing is read requirements. So in order to cut down on write amplification, you need to know how to encode deletes. Are you saying like ID 5 across the entire table is deleted? Or are you narrowly identifying where ID 5 is in the table and making a targeted delete? They have very different trade-offs at read time and write time. So a lot of these things are trade-offs of one another. So I think the best way to explore this area is to dive into those trade-offs. So let's look at the first trade-off. I set this up already. Direct writes. Assuming that you're going to write directly to a table, it's very simple, and it's I think the mental model that most people have, but it actually requires that you trade off a lot of these wants. So because we are batching together changes to this table, because of the double update problem, we actually have a really huge problem if we go and write directly to a table. The double update problem means that we can update a row only once for a given batch. So we're trading off this accurate history. We're essentially using a lossy format if we're writing directly to a table. It also increases write complexity. So if we want the property that we only update rows at transaction boundaries in the upstream system, we need to make sure that the boundaries used in the write to this table are at transaction boundaries in the upstream table. Well, how do we do that if we are taking data from 10 or 20 Kafka partitions and trying to apply it as a table at the same time? You have to coordinate and align the Iceberg table commits with the upstream table commits. And that's a lot more complexity. There's also a volume limit. It's actually really hard. So I think the simplest, I call this the hello world of CDC, is to actually use a changelog table. A changelog table is exactly what it sounds like. You take a whole bunch of data, just the changes, and you shove them into a table. Easy as that. And what the nice thing is, you get a historical record that is accurate. You have every single change in the entire table. You can use a filter on the transaction ID or the timestamp to time travel to any transaction. You get simple append-only writes that don't conflict with compactions later. It's high volume. It's great, except for the fact that you are deferring 100% of the work to read time. So you can't directly read this table. You actually have to use a window operation to apply all of the changes for all of time to the initial state of a row. So you can think of this as one far extreme of write amplification trade-off. You have almost zero write amplification and a very, very simple write path, but the most complex read path. So let's take a quick look at how this works. We create a table, account updates with our transaction ID, account ID, and amount. We can partition that so that we can automatically coalesce the data into larger files, but still keep track of it in time. It's really nice. And then we create a simple view. And in this case, you can see how creating the view is much easier because of how we structured those account changes to give us the accounts mirror table. So we select for each account ID, sum the amount as balance, and we should have a group by here. I don't know why I don't have a group by. Anyway, you group all of these account updates in time and you sum them together to get the final balance. This is often overlooked because most people want to write directly into a table and take on, without realizing it, all of the complexity of that direct write. But this, or actually a variation of this pattern, we used at Netflix for years. What we did was we would just regularly rewrite history. So we would trade history for the last few days or last few hours and only keep track of a very small slice of history. So we were able to take advantage of the fact that this is extremely low write amplification. And then we also got continuous time travel within the space of changes that we kept, very efficient writes, and it worked extremely well for a very long time. That was a really great pattern that I think is often overlooked because we want to do the direct write to the table. Well, the next pattern is that direct write. How do we take changes and merge them into a table? So this is a direct write into an analytic table. And this is also easy with the modern commands that we use to update and run big data workflows. So here we're using a merge. So we need to squash multiple updates into a single update to every row. And this is where that trade-off with the double update problem happens. So we squash each update into a single update. And then we have a very simple way of applying those changes. Merge into the accounts table using our updates from up here. And when we have a match, update the balance by the amount from the transaction log. So this is really simple. The nice thing about this is it supports custom logic. We can also, count the number of times a row was updated. Even if we lose the updates themselves, we can at least count the number of times, count the number of updates and know in a given batch whether we have lost any history. You can consume any data source with this. It doesn't just have to be UPSERT. And the nice thing is this is using position deletes. So we can use either position deletes for a lazy approach or rewrite data files for an eager approach and have a really nice pattern for read. Essentially, like we can trade off whether we want higher write amplification or more work at read time. And that's basically the next trade-off. So when we're doing this merge into the source table, or sorry, the mirror table, do we lazily merge? Do we write just the updates and then push that work to the readers? That has low write amplification because we're not rewriting whole data files. On the other hand, we end up creating, in our example table that had 4 buckets, 8 files every time we commit. So that's 4 delete files on average, depending on how many rows. If you're only updating 1 bucket, then you can get that down. But if you're updating most of the rows in the table, or even a double-digit percentage of the rows in your table, you're going to touch pretty much every bucket. So you create a lot of data files, but you defer work to the reader. On the other hand, you can also use a copy on write or an eager strategy where you rewrite files as needed. So every time a change comes in, if there's a row in a file that needs to be changed, you have to rewrite that entire data file. Now, this is actually great for readers. So it's a little slower at write time, and you might pay a little more to constantly be updating your table. But this is like combining the compaction operation where we apply those deletes to the files themselves and eventually clear out all of the the delete files that have accumulated. We can do that in one operation using a copy on write or immediate rewrite strategy. Now, like I said, this ends up rewriting the data files at that time. And that's really expensive. So, but the thing that drives the amount of work here is not just the strategy. The strategy here is deferring work. Do we want to do work at write time? Do we want to do work at read time? Because reads are slower if you use the lazy strategy. But the total amount of work depends on how often you're committing batches to this table. So that's the commit frequency trade-off. So if you commit more and more frequently, then you get closer and closer to real time in the source table. But it also creates a lot more work. So if you're using delete files, it creates a lot more delete files and basically makes you need to rewrite a whole lot more often. I think of this as it basically makes the merge strategy trade-off a whole lot worse. So if you are rewriting data files, you're rewriting them all the time. And if you're writing delete files, you're accumulating a ton of delete files because the frequency is so high. On the other hand, this is a really good way to make your, if you turn down your commit frequency, it's a really good way to save a lot of work and make pipelines simply cheaper. So if you only need a 2-minute latency on certain tables, definitely go and do that. If you can tolerate 15, 20 minutes worth of latency, then you're saving yourself an incredible amount of time. The second to last pattern I want to just briefly mention, because I don't think we have a ton of time today, is the Flink UPSERT pattern. So some people contributed this to Iceberg's Flink writer. I do not recommend using this. One of the things that Iceberg allows you to do, think about the trade-off that we just covered between lazy and eager updates. You're essentially pushing work earlier or later. You're deferring work to the reader or you're doing it now. The Flink UPSERT pattern basically does exactly that, only it defers work every single time it has a choice because Flink wants to be super fast writing things out to your table. So it uses equality deletes, which are deferring more work to read time. It uses, well, I guess it uses both equality and positional deletes. It doesn't sort so that it doesn't have to buffer data in memory. It wants to commit super often and exacerbate the amount of work that you have to do. And unfortunately, it requires just a ton of maintenance on your table. And who does that maintenance? Well, you do, either at read time when you pay the performance penalty, or you have to have a service or a scheduled job to go clean up the problems with the UPSERTs. In practice, this is just turning out to be the worst pattern because it requires so much maintenance, but doesn't educate people about the maintenance that is needed. So I highly recommend one of the two other patterns we've already looked at, either using merge in Spark or Trino, or just throwing everything into a changelog table and using a view to crunch down to the current state. That is actually a far better pattern and lasts longer and does a really great job. All right. Now, I think we've got a few minutes left. We've got 3 minutes left. I want to present the last pattern. So if we think about the two recommended patterns I talked about and go back to why CDC is difficult, we've got the changelog gives us a historical accurate record, time travel to any point in time, and transactional consistency. While the merge pattern give us a direct write, high volume, low latency, and this option of trading between read optimized and write optimized. So can we get the best of both of those, since these are clearly just separate things? And the pattern that I actually recommend that we're building on top of is actually to do both. It's a hybrid pattern, both merge and changelog. And in this case, what you do is you keep two tables. You write all of the data into a changelog table that's optimized for writes, gives you accurate historical record, continuous time travel, all of those things that you want. But then you periodically take those changes and merge into a downstream table. that gives you simple reads. It separates the concerns, and you can use even an optional view to merge the two for efficiency if you want, infrequent merges and super low data latency. So it gives you essentially the best of both patterns. It also gives you the worst of both patterns. So to be honest, like, you still have the eager and lazy trade-off. You still have the commit frequency trade-off on the table that you're merging into. Views can alleviate some of that by using the change log table as essentially the changes that you need to apply on top of the merge. But your pipeline is still pretty complex in this case. So you do have to do a bit more work, but it gives you all of the properties that we actually want. It gives you all of these properties. And I think that that's extremely important. The accurate historical record and time travel, and especially consistency across tables, absolutely something you want. All right. I think we're going to skip future work because I am coming up on time.